So I was asked about the exact citation concerning which aspect of quantum mechanics, so John Nash. So at some point he got versed into the theory and studied quantum theory, and he came up with this conclusion. Go back to the other one. Okay, so I will briefly review again the ABL rule. Apparently it was not very clear. And maybe if you have other questions on the first part of this morning's lecture, if you want to raise the issue, please do so now. So the ABL rule is concerned by the probability of obtaining. So we have a time t1, a time intermediate time t2, and a final time t2. So here we set the boundary conditions at t1 and t2 and t3, sorry, by choosing. So this is not a problem. We choose the preparation. We decide which state to prepare, and here we filter so we select on the outcome of the operator O3. So what the ABL rule is what is the probability of finding one of the eigenvalues of T2 once you know the, well, just put superscripts, never mind. Once you have fixed the boundaries, so once you have fixed this state and this state, and by probability here, you are just making standard projective measurements. And the result was here. So the probability of obtaining the state J are these probabilities of doing sequential measurements divided by the sum of all the intermediate results you can obtain. That's pretty intuitive that if you can obtain several results, the probability of obtaining a given outcome of O2 is just the relative probability of obtaining that one divided by all the different outcomes, the probability of all the different outcomes you can obtain. So there's nothing special except that if you apply this, so I'll try to explain things differently. If you want to know, when we find the probability, so you have three boxes instead, for instance, box 1, 2, and 3, A, B, and C. If you want to find the probability of finding the particle in box B with the fixed initial state given by this one and the fixed final state given by this guy here, then depending on the structure of the operator of the observable here, you will get different outcomes. So if you open the boxes separately, you can just choose it here. So if you open the boxes separately, you are sure to find the particle in box B. Again, this is due to the structure of my initial state, which has, I mean, the only common box to the initial and final state is B, so you're sure of finding the particle in box B. But if you choose another observable who has one eigenvalue corresponding to box B, but two eigenstates corresponding to box B, but not the others, because the others can be superpositions of boxes A and C, then you are not sure of finding the particle in box B. There's only 2/3 and not 1. And this is simply due to contextuality of quantum measurements, which is contextual relative to the observable you choose, and not just to the outcome you want to find. This is one of the consequences of the ABL rule, which again is only concerned by making projective measurements at some intermediate time and computing the probabilities of finding a given outcome with condition on having vector state 01 at the beginning and state 03 at the end of the process. So now we're going to get into sorry. So weak measurements. So this is different from the ABL rule. So basically, again, now you're getting used to this picture. We have some initial state, pre-selection, some final state that arises by making a projective measurement, and I want to know what can I say about the value of the observable A. So the idea of the weak measurement protocol is to couple another quantum system that plays the role of a quantum meter, and so it's an killer if you want, and the dynamical variable of this additional quantum system, quantum pointer, will give me some information on the value of A. So how do I do this? So at some intermediate time, there is a weak unitary interaction. So there is a unitary interaction that couples the system to this pointer, but it is weak. Weak means the coupling constant, the coupling strength is very weak. So if the coupling strength is very weak, then the system is almost unperturbed because, of course, the Hamiltonian interaction is very weak. And since it's almost unperturbed, well, the system just evolves almost as if there had been no interaction. And so you allow the system to evolve and reach the final state after a final projective measurement. So the aspect that we'll see now, we'll write down the equations, but the point is that when you make the final projective measurement that allows you to obtain psi f here, you're also projecting the state of the quantum pointer. Why? Because if you have a unitary interaction here, you will entangle the system in the quantum pointer. You have two quantum systems. So if this system state collapses, then you're also correlating the collapse of the system state to a given final state of the pointer. And this is how you are then able to go back to the pointer, see how its state changed, and then get some information on the value of A. So I'm repeating the same thing in a different way. So first of all, preselection, okay, state preparation, then weak coupling between the system A and a dynamical variable of the weak pointer. Post-selection, I do my projective measurement. I only keep the results for which I get psi f. Of course, I can get another type of result, but then I don't look at it. Just throw it away. And when I get psi f, I go back and read the weak pointer. Basically, I try to measure it, so I know its state, and what I will see, what we will show now, is that the weak pointer state has changed and reveals what is called the weak value of the observable A. This weak value depends on the initial state and on the final state, for the reason I just explained, because you have an entanglement, and when you project the entangled state to the system's final state, then you're correlating this final system state with a state of the quantum pointer. Yes. Yes. we will get to that a bit later. So the first step is the same as what we saw this morning for von Neumann model. The only difference is that the coupling constant is weak. So if it's weak, we are going to be able to do an asymptotic extension. So, same total Hamiltonian. So I'm neglecting the Hamiltonian of the pointer. So the pointer, I'm assuming, has no evolution, just to simplify things. Of course, the interaction I cannot neglect. So again, P is now a dynamical variable of this quantum pointer, just as in von Neumann's model. And again, G is a smooth function. Cannot be impulsive, as in von Neumann's model. In von Neumann's model, it doesn't have to be impulsive, but it could be impulsive. Here, it cannot be impulsive. And we will denote by U the unitary evolution generated by the free Hamiltonian, the system Hamiltonian is 0, and like I said, no sub-Hamiltonian for the point. Good, so preselection now involves preselection itself, progression of the state, and the total wave function is the system state, and now the pointer, which has an initial state that you know. And this is what I denote by phi. So I will again assume that the interaction takes place at TW, and the duration of the interaction is tau. So if you want, your function G is something like this. This would be TW. So the duration is, well, more or less tau, okay? So what is the total state of the system plus pointer after the interaction has taken place? Well, first, you evolve the system state vector up to time TW minus, well, just before the interaction starts. So that's what U does. We assume the pointer state doesn't move, so it stays there. Then, during the interaction, essentially only the interaction Hamiltonian is taken into account. So this can be justified by going to the interaction representation and so on. And this gives you the midpoint rule. So basically, you just write your system state at time TW, and you do this integration of the interaction Hamiltonian time. So there's nothing. You just integrate the time-dependent coupling constant, so you get an effective coupling constant here. So up to now, it's more or less what we could do with von Neumann's model. And now we're going to assume that G is small, which allows you to write the exponential to first order. No, T is not TF. T is a time after, so T is sometime after the interaction has taken place. And then you can, I mean, you can also assume it's TF, but in principle, you should write some additional free evolution to arrive at TF. Then there will be here projective measurement. But I will get to that just in the next slide, actually. Can see. So, what I just wrote down. So basically, after the interaction has taken place, you have again the free system evolution. We are neglecting any evolution for the pointer state. And just at TF, once all this has evolved to TF, we are going to make the projective measurements. So we assume there's an observable B with eigenstates that denote BK. And post-selection means that we only keep the results corresponding to a given eigenvalue, BK naught. And I denote this BK naught by K. So this is the post-selection. So again, if I measure B, I can get any eigenstate, any eigenvalue, any outcome, but it will only, post-selection means I only keep the result for which this is verified. So if this is verified, then after post-selection, I got Chi. And so my pointer state becomes this thing here. So I just projecting Chi over psi at TF. So here I just haven't done much except change the notation. So this is the forward evolution from TW to TF of this thing, but it's also the backward evolution of Chi from TF to TW. I'm just using this so that I use the interaction time, the time at which the interaction takes place, which is TW. Now I factor this. Then I factor this out. So this is just a scalar product of Chi and psi at the time of interaction. So that's why I was doing this, just to get both products at the same time. And I'm left with this thing here. Again, I haven't done anything. I have just factored and rewritten this like this. And now, since G is small, I re-exponentiate, meaning that this is taken to be the first term of asymptotic series of exponential. And this is how I end up with this term, which we can note. This quantity here is denoted as AW, and it's the weak value. So if there's no ambiguity, I will just use AW. If it's necessary to remember the specific pre-selected, post-selected states, then I will put as index subscript psi or chi just to make sure that there's no confusion. So what we have done here is just evolved the total system, asymptotic expansion assuming G was small, projection on the post-selected state which I obtained after measuring B. And this tells me that the pointer, the quantum pointer's wave function after post-selection, it is given basically by the original state on which acts some quantity here depending on the weak value. So basically, this is the position pointer state. This will give you a shift depending on the weak value. Remembering again that G is small. Thing. So the only thing that is left now to do is to extract the weak value from the pointer wave function. So this actually will depend on what type of wave function the pointer is. Typically, I will assume a Gaussian pointer. And so if my pointer is some more or less well or not well localized, we see here as wave function in position, then this will simply give you a shift of the initial Gaussian, a shift proportional to the weak value. So what is a bit tricky is when is this valid? So I'm doing an asymptotic expansion, neglecting more or less everything. So basically, if you really want to put very harsh conditions, you should do the expansion to any arbitrary order n, because you don't have any reason for an arbitrary observable. You don't know how the higher orders will behave. So here I'm just giving the example when you do the expansion to second order. So this is the first order that we just applied to get the weak value, and then I'm plugging in the second order to see when this first order cutoff is verified. So basically, if I don't know anything about my observable, I mean, I'm not specifying. I can specify anything about the observable. The parameters we're playing with can be only the width of your Gaussian, delta. So here's my Gaussian, and I think it's centered, yes, it's centered at 0. This one is my initial Gaussian, and so delta is a parameter, and the other will be G, which is the weakness of the coupling. So that's the only thing I can play with. Yes. So we will see that. Well, I don't know what actually I should, I should ask what actual value means, because what do you mean by actual value? You meant eigenvalue, or you meant? Because actual value is the value that the observable has at the time of the weak interaction. And in that case, it's of course not defined. The weak value is the only thing you can say about the actual value. So maybe it's not a value, but so we'll just in a moment I'll do the properties of. So if you do the second order expansion, so I'm just writing the same thing here. What you see if Gaussian is very narrow, and basically your pointer can only take values very near x naught, which is the center of the Gaussian. So I think here it's x naught equals 0. And in that case, it cannot work. I mean, the second term will be larger than the first term, so this asymptotic expansion, first order asymptotic expansion does not work. Now, if delta is large, this condition needs to be verified. So basically, G has to be small, and this cannot be big, so this will depend on your actual system, or actual observable, actual states. So usually, and something like this holds for each order n of the expansion. So basically, what you can, say as a general rule is that you need a wide, very wide meter state and very small coupling for this to work. Yes. No, because actually what really counts is the entanglement and the correlation. And this happens outside space-time. So time does not play a role, actually. So I think I will maybe have examples of Gaussian. So basically, this would be a very wide, let's say, Gaussian, and coupling. This to be very wide and relative to what we will see in a moment. Oh, so they're coming. So, if your pointer is used to make an ideal projective measurement, then you want, this is again your Gaussian, you want your pointers, they shouldn't overlap, so that basically when you will measure the pointer. Measure the pointer means that you will measure the position and it will collapse to one given position. You can discriminate the +1 region from the -1 region. In an ideal measurement, as we saw this morning, this is what you want to do. Now, if instead of having, so this means that the Gaussian has to be sufficiently narrow. If you have, instead of narrow Gaussian, so this would be, let's say, -1. This would be +1. So we have two Gaussians like this. Then you're in what we call this morning a non-ideal measurement case. And in that case, you can get anything. So here you have the -1 and +1 eigenvalues. You see them here, -1, +1. So here, actually, this is the result of the interference of two Gaussians of this type. Once you do the projective measurement of the system, then you have these two Gaussians that interfere. So you have this one times some coefficient plus this one times some coefficient, and then when you look at the result, this gives you that kind of behavior. So the weak measurement is an unideal measurement, but in a very special, specific regime, in which you don't get anything, but you get the weak value. And this is a characteristic of measurements, is that it's totally universal. It does not depend on the type of pointer states. For an arbitrary non-ideal measurement, that will depend on the type of pointer states you choose, on the type of couplings and so on. Here, in the weak limit, well, you just have a single. The superposition gives you a single Gaussian, which is just displaced by the weak value. So it's a single broad peak. So the only, so this is one of the characteristics I will talk about in a moment. So here you have the eigenvalues of the observable, ±1, and the weak value is the center of this very broad peak. And as you can see, it doesn't sit on the eigenvalue. It can be anywhere depending on the value of the weak value of the definition of the weak value. So I will mention in a moment that the weak value, as you may have seen from its definition, is a complex quantity, and actually the displacement is the real part. So what I just wrote is correct, but if you talk about the displacement of the Gaussian, it's only the real part that counts. The imaginary part does some other things. So really, it's the maximum is the real part of the weak value. So what is a weak value? Talk about this frequently. So operationally, it's the value indicated by the weak pointer readout. So I haven't said much about that, but okay, you just apply the protocol that I just gave you, and then, yes, there is. So I think I will give it just, yes, a bit later. So the weak value, well, as we just saw on one illustration, it's different from the eigenvalue. Actually, it has to be different. Except if you post-select on one of the eigenstates of the observable you usually make. And so it can lie outside the eigenvalue range. And so it's universal, as I just said. It doesn't depend on the specificities of the measurement, which would be the case for any other type of non-ideal measurement. So these weak values were introduced almost 30 years ago in this paper by Arndt, Albert, and Weidman, this provocative title, how the measurement, the component of the spin The spin 1/2 particle can turn out to be 100. So how? It's because the value can take, can be very large, much larger than the eigenvalue. So there has been an increase in the number of works because actually this protocol can be implemented experimentally, and so there has been increasing interest when several experiments were made. So it's interesting to investigate foundations because it allows you to ascribe a value where you would think that the standard formalism tells you can do anything. So that was a little bit the aim of all the paradoxes I showed you this morning, is that in principle you can't say anything, and here, well, you don't, maybe there's some controversies on the meaning exactly of what it can tell you on the system, about the system. At least, especially when there's nothing else we can do, well, people have been doing measurements and obtaining results. So now the first property. So if you look at the expectation value in this state psi TW, which is the system state at the time of the weak interaction. So this, the first line you know, it's of course probability to obtain an eigenvalue times the eigenvalue. This gives you the expectation value. But you can also rewrite this as the probability to obtain a given post-selected state times the weak value from that initial state to one of the given post-selected states. So you can obtain this, maybe we can do this very easily. Actually, you just write the expectation value. You insert the identity twice. First, unitary evolution, and then all the post-selected states. So first you insert, you have UU, and then you insert here some of the post-selected states. Here I will write it. This gives you the evolution, backward evolution of the post-selected state K from TF to TW. Then you simply divide both, both sides by 1, which basically by 1 is this thing. And so then, basically, if you divide this by this, you just get the definition of the weak value. and the probability of reaching the final state. So of course this this is the backward, again, this is the final state, the post-selected state, K, evolved backward in time from TF to TW. So we take the scalar product of everything is taken at the time of the weak interaction. So your expectation value, your usual expectation value, which is a sum over the eigenvalues, the eigenvectors, here becomes a sum over all the post-selected states you can reach times the weak value. So the weak value plays very much a similar role. So the last step here, so it's why it's only the real part, is that since the expectation value of a Hermitian operator is real, then this the right-hand side has to be real also, which means that the complex part, when you make this, when you sum over the final selected states, the complex part vanishes and you're only left with the real part. So again, the expectation value, either you measure the observable, A, in the state psi, and then it's the usual formula that applies. But if instead of measuring directly A, you measure some other observable B, and then you sum over all the states you can get over the final eigenstates of B, which we call here K, which will BK, which we'll call them BK, then it's the probability of reaching from the initial state each of these states BK times the weak value. So we just saw that only the real part was related to the expectation value of your observable that you're weakly measuring. Now, if your weak value is real, then assume this is the average position of your pointer before weak interaction. This is the final position, final average position of the pointer after the weak interaction has taken place, and post-selection. Then in that case, if AW is real, we just have a simple shift of the pointer. So that's pretty obvious from this thing. Now, if AW is complex, but your pointer is real, then you have the same thing, but for the average position, but only taking into account the real parts. And you also have a shift in the momentum. So this shift represents the imaginary part represents the back action, the momentum. It's not related to something having, it doesn't have anything to do with the observable A. It doesn't give you an idea of the observable A. The back action actually, it's very much dependent on the type of pointer states you have. So usually it goes to 0 very fast, but it really depends. It depends on the distribution of the pointer weight function. Then you can have a W complex and also a complex pointer. For example, if you have a Gaussian pointing in some a Gaussian position space pointing in some specific momentum, it will be a complex function. And in that case, you also have a change in the position of the observable related to the change in variance. So usually also this is negligible. So the important point here is that the real part of the weak value is related to the weak measurement. The imaginary part has been a little bit more, this is rather straightforward, and one of the arguments is the one I gave you on when you look at the expectation value. The imaginary part has been a little bit more discussed because it's related to the mean disturbance. So it's not, people do not necessarily agree on how it's related to this disturbance. So you'll always have to keep in mind that weak interaction means that only a tiny fraction of the system state interacts with the pointer. If I don't introduce you mean? Yes, so actually I want to, this is due to the fact that this thing is equal to this one. It's equivalent to what you say. So basically why I introduced this unity operator, because I want to emphasize the fact that the process I'm making here, these two expressions are equal, but I want to emphasize the fact that the weak interaction takes place at time tw and the post-selection at times tf. So basically what I want to do is introduce the post-selected, the identity, the resolution's identity of the post-selected states at time tf, and then remember that there is an evolution from time tw to time tf. But of course, this scalar product is the same if you take it at time tw and time tf. From the mathematical point of view, it's irrelevant. You can take it at tf or tw, but it's important physically to understand that the meaning, I'm trying to emphasize on the meaning of the expectation value given in terms of the weak value. Because the process is, I start at ti with some given state. Then here I'm doing a weak measurement at time tw. This is where the entanglement takes place. Then at the end, I do a projected measurement of B, and I can get any of the results bk. And this happens at time tf. So physically, this means that the expectation value is taken at this time. And it's equal to the weak value where the post-selection takes place at time tf. This is why I insist on it. Weak value properties in the imaginary part of matrix. Okay, so the eigenvalue bounds. So we just saw that the weak value, the real part of the weak value, is not constrained by the eigenvalue bound. So actually, this is necessary and has nothing to do with quantum mechanics, so there's a confusion even in some high-profile journals. Basically, if you have an average, so I'm looking here now, that you can write in terms of two different probability distributions, then if you want to find the same average, your AK cannot be equal to the A-tile K. This is simply not possible, and this is exactly what we are doing here. We're just writing on the same average. The probabilities are different than in the expectation value. This expectation value is for the weak values, and so the quantities cannot be the same. So I think so. This is just a simple example. So I just gave this example because of the confusion, but maybe if you haven't heard too much, I shouldn't insist. Basically, I mean, from the classical point of view, if you have a different, so you wouldn't, classically would have eigenvalue. You would have a different dynamical variable, which has, let's say, a real value and a perturbed, a disturbed value. This is what would happen classically. So what I'm doing here is I just imposing the fact that the average of the perturbed value, which is a tilde, is equal to the average of the real dynamical variable. And assume that this is measured by some apparatus. A tilde is measured by some apparatus, which gives me, so I know that a tilde is equal to plus or minus 1. I also know that a plus minus is dichotomic, but I don't know the real value of a plus minus. I just know that the open calibration, there is some probability that I will get a tilde plus if the real value is a plus or a minus. So from the observation of the frequencies and imposing that the average is the same, then we can obtain the real values, the unperturbed value, the not perturbed values of A, which can, this numerical example would be 0.5 and minus 8, whereas I observe 1 and minus 1. This is simply due to the fact that I impose this. So the fact that the weak value lies outside of the, can lie outside of the bounds of the eigenvalues is not, as such, a specific quantum phenomenon. However, what I wrote here, what is specific to quantum mechanics is how the weak values arise. This is very specific to quantum mechanics. Why? Because if you have a classical dynamical variable, then to have a genuine A and the perturbed A tilde means you do have a perturbation. So you have to perturb your system so that your A is transformed into a tilde. Here, it's not the case. Here we have a very weak coupling. You have entanglement and you have interference. This is what really makes the weak value quantum. It's not the fact that it lies outside of the eigenvalue range. So I'm sorry to insist on this point. Okay, so since we were asked to give tutorials, what I would suggest, so I have several, so I think I have several exercises that we can do. So what I suggest, and three maybe, I have two here and a third one I didn't have time to note. So what I suggest is that we work out these exercises together, and for those who wish. And so this will probably take us up to the end of the lecture. So I will not do a special tutorial lecture at the end. So I will do it now. And so those who don't wish to do it, maybe they can just leave. And so I will just maybe read the first problem. So the aim is for you to compute the weak values and kind of get familiar with the weak values. So you have to apply the formula. And the second, so the second is also a little bit more difficult, and the third would be the three-box paradox, computing the weak values for the three-box paradox. So we'll read the problem, then you decide if you wish to do it now or just listen tomorrow to the solution. So the first exercise is just computing the weak values for the spatial projector. So we go back to what we saw this morning, the delayed choice. So basically the interferometer with or without the LCD splitter. We'll just assume there is a phase shift here on path 1. So path 1 is the one leading to D1, path 2 is the one leading to D2. So this is the pre-selected state at the entrance. So I will assume it's a narrow wave packet, but this doesn't really matter. And I will just assume that for purpose of doing something, that here each beam splitter gives pi 2 phases for reflection and just 1 for transmission. So just in order to do the exercise. So this gives you the transformation after the first beam splitter. So you know that the possible final states are either chi1 if d1 clicks, or chi2 if d2 clicks. So we now assume we can put quantum pointers along the path, weakly coupled to the electron. Let's say you have a neutron, an electron, whatever. And so you couple, for example, on path 1, this projector, the projector on path 1 at TW, so assume TW is some fixed time here. So that's when the interaction takes place. So if you wish, I simply here I would have a pointer measuring pi 1, well, we could couple to pi 1. So P would be the P of the pointer. So what I want you to do is first to take the interferometer without the second beam splitter and compute the weak values for both projectors when the post-selected state is chi1 and when the post-selected state is chi2. And then do the same thing for the beam splitter with the interferometer with the beam splitter. I'm not writing the evolution operators because it's not trivial. So you start from the definition and you apply this to pi 1 and pi 2. Both configurations. write the wave function. So you don't see, we'll put it maybe up there. So you write the wave function, system wave function at the time of the weak measurement. You don't see, okay. Yes, so I write it here. So it's not there. Okay. So basically, you start from the definition, which takes place at TW. So here, since I use TI and TF, I just need to make the evolution. So this gives you the wave function at the time of the weak measurement. Then you apply, well, pi1 first. So if you apply pi1, so this will, of course, tell you this term. What I've written up there. So then you're left with this. This, of course, so you're finished, because then you just know the scalar product here. Here. And you obtain 1. Just straightforward application of the definition of the value when, so again, so selecting here on D1. So the result is that if I select only one, so again we assume we have some pointer here that interacts with the system. So what does this mean? If I have a pointer, an ankila, another quantum object that interacts with the system, the state, the quantum state of this pointer will be modified if I place the pointer on arm 1, but will not change if I modify the pointer, if I place the pointer on path 2. This is path 2 and this is path 1. Now, if I push select on D2, if I push select on D2, you can do the computation. Then you get the opposite. So if I push select here, the state of the pointer placed on arm 2 is modified, but the state of the pointer placed on arm 1 is left unchanged. So we can interpret this as saying that the weakly pointer on arm 1 sees the particle when we have a final post-selection detector 1. But since this pointer is left unchanged, we have no trace of the particle along arm 2. And it's the opposite when the final detection is on detector 2. The weakly interacting pointer on arm 2 has now changed, the state has changed, and you can check this by measuring the wave function, the state of this pointer, and not while in the pointer on arm 1 has been left unchanged. So it is very tempting to conclude that since this measuring apparatus has measured the passage of the particle it has only seen the particle on arm 1 here, which means there's a correlation between detection here and pointer motion here. Whereas here the pointer is just left untouched because, well, there was an interaction, there's a coupling, but it has no effect. So does that sound reasonable? And it's consistent in some sense with Wheeler's first conclusion that when there's no beam splitter, the particle takes path 1 when detected by D1 and path 2 when detected by D2. This is what we just saw, what we saw this one. So now I think there was the second part, which basically is the same problem, but now we have the beam splitter. So, basically, it's the same in both cases, actually. Okay. So if you have a state launched from here, so good. If you launch a state from here there's no beam splitter. So just imagine you're launching, I don't know, Gaussian from here, then that's what it does. A state evolving backwards in time, it does this. But it's the same thing. B2 is if you launch a state from here, backward in time, it goes like this. There's no beam splitter, nothing happens. Nothing happens here. This state launched backward in time from D2 can only go through. So basically, you don't have to do this. Basically, you are assuming you start from an initial state, you go forward in time, you have an interaction, you go forward in time. But what we just saw formally is that this evolution operator here can be read as chi1 going backward in time. So this is just, so if you parse it this way, it's initial I here. Then evolution up to TW here, and then weak interaction, and then again evolution up to 1 because I select on 1. So this is just parsing forward in time. Now I can also read it this way. Don't have to read it this way, although the weak values were introduced to give some substance to the fact that we could read it this way. So I'm not talking about this aspect now. Maybe I will talk at the end of the lectures to avoid some confusion. But you can read it this way as the weak value arising from at the intersection of a wave that evolves backward in time, because this is what it does, Tf up to Tw, and the wave that has evolved forward in time from Ti to Tw. So this is possible. Now, some people, so in particular those who came up with the weak value, they think that this is what really happens. I think that this is why their formulation is called time-symmetric quantum mechanics. They are very bothered by the fact that you can choose the preparation of the state, but you cannot choose selection in the sense that when you make the last measurement, the outcome is random. So they think that there is actually a predetermined wave coming from the past. Right, so, okay, I don't want to mention this now. I think it's better to understand the weak values, and then we can dwell into this time-symmetric. Yes. Now let's add a beam splitter here. beam splitter here does is that it sends you a combination of psi 1 and psi 2 on each of the two outgoing arms, right? So we have time to finish. The difference is, of course, that the so let's look at post-selection on D1 first. So if there's a beam splitter, then what happens is that the final state evolving backward in time is now taking both arms. That's the I, because I said that we assumed that when it gets reflected, there is an I factor. So that, so that the psi evolved to psi 1, so EI phi, so that's the phase shift, gets the I phi, plus I psi 2 because of the psi 2, the I because of the beam splitter. This is just a convention. A beam splitter can do something else. Usually the reflected and the transmitted waves are dephased. So if we look at post-selection on K1, which is the one on the top here, so phi 1 gives you, well, here you just compute the scalar product. And basically, the message is that both pointers change the state. So there's a change in the quantum state of both pointers when we are in this configuration. The same thing post-selection is on D2. The same reason again is that because of the beam splitter, the post-selected state evolves along both arms, or if you wish, if you want to keep to the forward in time picture, then it's because of the beam splitter. You have an outgoing part of 1 and of 2. So here it's probably psi1 minus psi2 here and psi1 plus psi2 here. So this gives you, this allows you to compute the weak values and to see that this tells you there is each pointer sees something on the path in which it's going. So then I don't know if it's correct to say that both pointers see the particle, because then it's maybe not a particle. It's not as, not if you follow the meaning, it has classical mechanics. But again, it's pretty consistent with what we have seen according to Wheeler. So if the beam splitter is there, then weakly interacted pointers will see the particle or the wave on both sides. So by the way, the first case, we had weak value equals 0 or 1, and those are the eigenvalues. In this case, it's even the real part does not correspond to an eigenvalue of the projector operators. So the weak values are different from the eigenvalues, and the reason here, of course, is that the weak values are non-zero on both paths. That was the first example, so I don't know if you have questions or maybe you finish. You see that projective measurement tells us that the particle is in one or the other arm. And a weak measurement allows you, depending on the setup, to answer, well, there is a particle on both arms. Since I only have 5 minutes left, I think I will not start with the second example. Maybe we can just at least have a look. There are no questions on this. So this is a computation of the weak values of a qubit or a spin, as you wish. So basically, we prepare the state, the initial state, in an arbitrary direction, on an arbitrary direction of the Bloch sphere. Then we assume there's some quantum pointer in the state that interacts weakly with the system observable, which is now the spin, sigma z. This is the interaction Hamiltonian. So basically, these two are constants. Actually, it's just, this is typically what happens in a spin in a Stern-Gerlach. V would be the magnetic field, and U the general magnetic ratio. They're just constants. We're just interested here is Q, which is the pointer variable, and sigma z, which is the system observable we want to measure with. course, as you know, it's plus minus 1 to make a strong measurement. And the post-selection condition is plus x. Basically, what we want to do is compute the weak value. Then look at the specific cases when theta is equal to pi over 2, and also look at what happens to the real part of the weak value when phi tends to pi. And the second part is to do look at the total wave functions evolution exactly, forgetting about the weak values, and then compare both approaches. This is how you can really understand what the problems are about. In this case, you can exactly solve, let's say, the exact solution, and then you can compare the result given by the weak value and the result given by the exact pointer. Alpha is here, so actually it's just UB tau is just alpha to simplify the notation. So if you don't have any questions, we can stop here and continue tomorrow. And then we'll to compute weak values? Well, no, we don't use the Born rule. Actually, it's a transition amplitude. It's a ratio of transitions amplitude with and without the interaction. Transition amplitude with some interaction, and this is without the interaction. Yes. Yes. Well, the probability is given by the Born rule in this case, of the initial state to one of these post-selected states, assuming there's no interaction. This is because to first order, the weak interaction does not change the post-selection probability. What, sorry? Theta here. So this is a general, the general spin state, which is an eigenstate along a specific direction of the Bloch sphere, which is given by theta and pi. So this is just an eigenstate. So this is just the eigenstate of a component that would point in that spin component that would be directed on the direction of theta pi. It's just a general spin state. So thank you very much. See you tomorrow.